Consider the bar shown in figure. Determine the nodal displacement and element stresses and support reactions. Determine the nodal displacements, element stresses and support reactions. This is the bar question. So here in this question, some 3.5 distance is mentioned from the second stepper bar. So here in this diagram, so we have 5 dimensions, that is first one, second one, third one, fourth one, and this one is 3.5 distance from the second bar element. So here in this first bar, cross sectional area 250 mm square, and second bar cross sectional area 400 mm square, and the entire bar E is equal to 200 into 10 power 9 Newton per meter square. So here in this question, so here 150 mm, 150 mm, 200 mm, 200 mm and 3.5 mm, and areas are, cross sectional areas are in terms of mm. So all dimensions are in mm. So here in the C value, so Newton per meter square, we need to convert Newton per meter square in terms of Newton per mm square. So first of all we need to write dimension conversion. Coming to the solution, so here A1 is equal to 250 mm square, A2 is equal to 400 mm square. So here E is equal to this is given data. E is equal to 200 into 10 power 9 Newton per meter square. So here we need to convert Newton per meter square in terms of Newton per mm square. So here that equal to 200 into 10 power 9 whole divided by 10 power 6 Newton per mm square. So here E is equal to 200 into 10 cube Newton per mm square. This is the E value. So here all dimensions are in mm. So coming to the given problem, so here 2 stepper bars is there, that is first one and second one. So in the we need to check. So here 4 dimensions are there. So here some linear diagrams. So here some point load along the x direction, some point load along the x direction. So here one dimension is there, that is 150 mm, that is 150 mm. So here node 1 and node 2, node 1 and node 2. So here node 3, that is 250 mm distance from the point load. So here again point load P, that is 4th node, and last one 5th node. These are the dimensions. 3rd node to 4th node 200 mm, and 4th node to 5th node 200 mm. This is the linear diagram for the given problem. So here some fixed end is there, some fixed end is there. So here the distance is 3.5 mm. 3.5 mm. So here how many number of elements is there? So here total number of elements, first element, second element, third element and fourth element. So total 4 number of elements. So here how many number of elements is there? So here first element, second element, third element and fourth element. So coming to the next step, so here elements, nodes, elements and nodes. So here first element is having 1 and 2 nodes, second element is having 2 and 3 nodes, fourth element, third element is having 3 and 4 nodes, fourth element is having 4 and 5 elements. So here what is the common nodes? So here second node is common and third node is common and fourth node is common nodes in the given diagram. So first of all, so the element stiffness matrix, first of all we need to calculate element stiffness matrix for the first element, element stiffness matrix for the first element. This is the first step and this is the second step. And coming to the next one, so element stiffness matrices, element stiffness matrices. Element stiffness matrix. What is the formula for element stiffness matrix for the given bar? So here element stiffness matrix K equal to AE by LE 1 minus 1 minus 1 1. This is the standard formula for the one dimensional bar element. So here coming to the first one, so we need to calculate element stiffness matrix for the first element, that equal to, so here what is the A value? So entire, this is the A1 value, and this one is the A2 value. So here we need to consider, this is the A1 is the cross sectional area for the first bar and A2 is the cross sectional area for the second bar. So here A1 is equal to 250 mm. So 250 into, what is the E value? E value is, we can convert it into Newton per mm square, that equal to 200 into 10 cube whole divided by length of the first element. So here what is the length of the first element? Length of the first element 150. So 150 into 1 minus 1 minus 1 1. 1 minus 1 minus 1 1. So here what is the value for 250 into 200 into 10 cube by 150? So here 333.33, here 333.33 into 10 cube, 1 minus 1 minus 1 1. 1 minus 1 minus 1 1. So here coming to the second element, so here second element is also same, that equal to 150 mm length. So here cross sectional area of the second element is 250 mm into E value 200 into 10 cube whole divided by 150. So here 1 minus 1 minus 1 1 is equal to same value. So 333.33 into 10 cube minus 1 minus 1 1. So here what is the values of element stiffness matrix for the first element? So here the nodes are 1 and 2. So we can represent 1 2 1 2. What is the second elemental nodes? 2 3. So here 2 3 and 2 3. 2 3 and 2 3. Coming to the third element. So here element stiffness matrix for the third element is, so here this is the third element. What is the cross sectional area of the third element? So here cross sectional area is 400, that equal to, we need to substitute A is equal to 400 into E value is same, that equal to 200 into 10 cube whole divided by, what is the length of the third element? So here L3 is 200 into 1 minus 1 minus 1 1. So here K3 value is 400 into 10 cube. K3 value is 400 into 10 cube 1 minus 1 minus 1 1. So here coming to the fourth element, the stiffness matrix is, what is the value for cross sectional area of the second element? Sorry, cross sectional area of the second bar. So here AT is equal to 400, that equal to 400 into 200 into 10 cube whole divided by length of the fourth element, that equal to 200 1 minus 1 minus 1 1, that equal to same value. So 200 get cancelled. So here 400 into 10 cube 1 minus 1 minus 1 1. So here the element stiffness matrix third element nodes are 3 and 4. So 3 4 and 3 4. So here what is the nodes for the second element, fourth element? So fourth element nodes are 4 5 4 5. So here in this equation, how many number of elements are there? So here 4 number of elements and 5 number of nodes. So coming to the global stiffness matrix, so here global stiffness matrix capital K is equal to how many number of elements? So here 4 number of elements, that equal to K1 plus K2 plus K3 plus K4. Global stiffness matrix or otherwise assembly stiffness matrix. So here in this global stiffness matrix we need to substitute node 1, node 2, node 3 and node 4 and node 5 values. So here 1, 2, 3, 4, 5. So here this is the 5 by 5 matrix. Here this is the 5 by 4 matrix. So here in this global stiffness matrix, we need to substitute these K1, K2, K3 and K4 values in the global stiffness matrix. So here the common factor is 10 power 5. So here the common factor is 10 power 5. So in the first row first element 3.33 and the second row first element minus 3.33. So here second row first one minus 3.33 and this one 3.33. This one 3.33. So in the second element, so here we need to add 3.33 plus 3.33. So what is the 2 element? So here the 2 element is minus 3.33. What is the 2 element? Minus 3.33. And what is the 3 element? 3.33. So this is the second element values. So here in this equation in this global stiffness matrix, I substitute first elemental values and second elemental values. Coming to the third elemental values, so here third elemental value is, what is the third element value? I think 400. Here what is the third elemental values? So here the third elemental values, third row, third column corresponding value 4. So here minus 4. So here minus 4 and 4. This is the third elemental value. Next fourth elemental value. So here fourth elemental value is also same. So here in this fourth row, fourth column, this is the common one. So plus 4. -4, -4 and 4. So remaining values are zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is the global stiffness matrix. So here this is the first stiffness matrix, and this is the second stiffness matrix, and this is the fourth stiffness matrix, and this is the fourth stiffness matrix. This one first stiffness matrix K1, K2, K3 and K4 like this. So here this is the common node. So here this is the common node factors. Coming to the next one, the finite element equation that equal to KQ equal to F. The finite element equation KQ equal to F. The finite element equation KQ equal to F. Finite element equation KQ equal to F. Finite element equation KQ is equal to F. KQ equal to F. So here the K value is, we already calculated, 10 power 5 into what is the one value, 3.33 minus 3.33 and minus 3.33, and what is the common node? 6.66 0 0 0. So next one minus 3.33 minus 3.33 0 0, some 7.33 minus 4 0 0 0 minus 4 8 minus 4 0 0 0 minus 4 and 4 minus 4 and 4. So here this is the 5x4 matrix. Coming to the nodal displacements, so here nodal displacements are Q1, Q2, Q3, Q4 and Q5 is equal to, what is the forces? F1, F2, F3, F4 and F5. This is the finite element equation. This is the stiffness matrix, global stiffness matrix K. So here nodal displacements Q1, Q2, Q3, Q4 and Q5, and force vectors F1, F2, F3, F4 and F5. So here first node, second node, third node, fourth node and fifth node, first node, second node, third node, fourth node and fifth node. So here what are the displacement values? So here I can write so here one fixed end, so here this is the Q1 point load, so here this is the Q2 and this is the Q3, and so here again point load, this is the Q4 and here Q5. So here this is the Q5, but in the given problem some distance, that is 3.5 mm is there, so that's why Q5 is represented with 3.5. So Q5 is represented is 3.5. So here Q1 is at fixed end, that equal to Q1 equal to 0. Q1 equal to 0. So here in this equation Q1 is equal to 0 and Q5 this one. The distance from the fourth node, fifth node to fixed end. So here 3.5. Here 3.5. So here what is the forces? So here the fixed end. So here force 1, force 2, force 3 and F4 and F5. So here the point load is F2. That means F2 value is 300 kilonewtons. F2 value is 300 kilonewtons. That equal to 300 into 10 cube. So here kilonewton. So kilo means 10 cube. So F3 is at fixed end. So here F4 is, what is the value? 600 kilonewtons. So here F4 is 600 kilonewtons, that equal to 600 into 10 cube. So here we can substitute the boundary conditions. We know the boundary conditions are. So here Q1 equal to 0 at fixed end, Q5 is 3.5 mm from the fixed end. Q5 is 3.5 mm from the fixed end. So here, so in the elimination approach, the stiffness matrix K is modified by 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 deleting row and column, deleting row and column, corresponding to the fixed degree of freedom, fixed degree of freedom. Thus K is modified by, capital K is modified by deleting the first row, first column, deleting the first row, first column, and fifth row, fifth column, fifth row, fifth column of the original stiffness matrix K, of the original stiffness matrix original stiffness matrix K. K is modified by deleting the first row first column and fifth row fifth column of the original stiffness matrix of the K value. Also F is obtained. Also F force is obtained by deleting the force is obtained by deleting the first component, deleting the first component and modify the fourth component, modify the fourth component. So here force is obtained by deleting the first component and modify the fourth component by, so here we need to calculate F4 value. So here what is the F4 value? 600 into 10 cube plus 4 into 10 power 5 into 3.5. So here again I am explaining. So here the boundary conditions are Q1 at fixed and 0 and Q5. So here Q5 some distance is there, therefore 3.5. This is the Q5 value 3.5 mm. In the elimination approach, by using elimination approach, the stiffness matrix K is modified by deleting row and column corresponding to the fixed degree of freedom. So here the fixed ends are, so here the displacements Q1 and displacement Q5. So here some 3.5 mm distance from second bar. So here the K is modified by deleting the first row first column and fifth row fifth column of the original stiffness matrix, that is K value. So also F is obtained by deleting the first component and modify the fourth component. So here this is the first row first column. So here this is the first row first column. So here fifth row fifth column. So here in this matrix, after applying elimination approach, after applying Gauss elimination approach, so here 3 by 3 matrix is there, but so here in this problem 3.5 mm is mentioned from the fifth node. Mentioned from the fifth node. That's why I am calculating F4 value. So here what is the F4 value? What is the F4 value? 600 into 10 cube F4 plus what is the fifth row fifth column value? So what is the fifth row fifth column value? 4. So here fifth row fifth column into, so here what is the fifth row fifth column value? This is the fifth row fifth column value, 4 into 10 power 5. Fifth row fifth column value, and what is the distance from the fifth node? What is the distance from the fifth node? 3.5. So here 4 into 10 power 5 into 3.5. That equal to, what is the value? 600 into 10 cube plus 4 into 10 power 5 into 3.5 is equal to 2000 10 power 3. 2000 10 power 3. So here 600 into 10 cube is force 4, F4 value. So 4 into 10 power 5 is the fifth row fifth column value into distance between the fifth column to fixed rate. So here this is the important one. So F4 plus fifth row fifth column, that is 4 into 10 power 5. So here 4 into 10 power 5 into the distance between the fifth element to fifth node to fixed rate, that equal to 3.5 mm. So here this is the final value, that equal to F4 is equal to, therefore F4 is equal to therefore F4 is equal to 2000 into 10 cube. F4 is equal to 2000 into 10 cube newtons. The modified finite element equation, the modified finite element equation the modified finite element equation the modified finite element equation. So here modified FE equation. So after applying the Gauss elimination approach, so here this is the matrix, and what is the F4 value? 2000 into 10 cube. What is the F4 value? 2000 into 10 cube, 2000 into 10 cube, and what is the F2 value? 300 into 10 cube. F2 value 300 into 10 cube. So what is the Q3 value? So here Q3. So here this is the fixed rate, that's why I am considering F3 is equal to 0. F3 is equal to 0. So here we need to calculate displacement value Q2, Q3 and Q4. Q2, Q3 and Q4 value. Q2, Q3 and Q4 values from the above matrices. So here 10 power 5 is the common factor. So here we need to calculate in the, so here calculation operation. First of all we need to clear all the stored data, that equal to mode shift plus mode, that equal to press 3 all. So reset, enter the calculator. So here I am calculating modified finite element equation. So here I am calculating modified finite element equation. Finite element equation. So here press shift button. First press the mode 1, 2, 3. Press the mode button in 3 times, that equal to equation. Press 1. And what are the unknown terms in the given modified matrices? 3 unknown terms, that equal to Q2, Q3 and Q4. Q2, Q3 and Q4. So 3 unknown terms, that means enter 3. So here what is the A1 value? So here what is the A1 value? So A1, A2, A1, B1, C1 and D1. So on A2, B2, C2 and D2, A3, B3 C3 and D3. So here we can substitute in the modified matrices. So here what is the A1 value? 6.66 into 10 power 5. So in the Calci operation some exponential function is there. So here exponential 5, that is E5. E5 equal to, what is the B1 value? Minus 3.33 E5. And what is the C1 value? 0. What is the D1 value? 300 E cube. So what is the A2 value? Minus 3.33 E power 5. What is the B2 value? 7.33 E5. So what is the C2 value? Minus 4 E5. What is the D2 value? That equal to 0. What is the A3 value? 0. And what is the B3 value? Minus 4 E5. So what is the C3 value? 8 E5. And what is the D3 value? That is 2000 E cube. So here some X value and Y value and Z values is there. So here the first one Q1 equal to 2.019. 2.019. So here Q2 is equal to 2.0193. 2.0193. And second one Y is equal to, so here what is the Y value? Q3. So Q3 is equal to 3.1377. 3.1377. And last one, what is the Z value? 4.0688. This is the Q4 value. 4.0688. So here units are m. So here this is the nodal displacement values Q1, Q2, Q3, Q2, Q3 and Q4. Nodal displacement values. First question. Nodal displacements Q1, Q2, Q3, Q4 and Q5. What is the Q1 value? Fixed end, that equal to 0. What is the Q5 value? 3.5. So what is the Q2 value? So we already calculated 0.0193. What is the Q3 value? 3.1377. So what is the Q4 value? 4.0688 units mm. So these are the nodal displacement values. Coming to the next question. So element stresses. Coming to the next question. Element stresses. We need to calculate element stresses. We need to calculate element stresses. This is the first question and this is the second question. What is the second question? Element stresses. Element how many number of elements? So here 4 number of elements is there, that equal to bound sigma 2, sigma 3 and sigma 4. So here what is the formula for element stresses? So here element stresses, stress is equal to EBQ. Stress is equal to EBQ. So here BQ is the strain element. So here E is equal to stress by strain, that equal to E equal to stress by BQ. So stress is equal to EBQ. So here B is equal to, one by LE minus 1 by LE minus 1. So here stress 1 is equal to EBQ. So here what is the E value? So we already calculated 200 into 10 cube Newton per mm square. 200 into 10 cube Newton per mm square. So here what is the E value? 200 into 10 cube into 1 by LU. What is the length of the first element? So here length of the first element is 150. So 1 by 150 into minus 1. This is the B value. And what is the Q value? So here in the first stress, how many number of nodes are there? So here first node and second node. So here the displacements are Q1 and Q2. So here Q1 is equal to 0, Q1 and Q2, Q1 equal to 0, Q2 is equal to 2.0193. 2.0193. So here stress 1 is equal to 200 into 10 cube whole divided by 150. So here minus 1 into Q1 that equal to 0, minus 1 into 0 plus 1 into 2.0193 that equal to stress at the first element is equal to 2692 Newton per mm square. 2692 Newton per mm square. Similarly, we calculate stress at second element that equal to 200 into 10 cube. Length of the second element is L2 same. So here 150 minus 1 and here second element. So here 2 and 3. So Q2 and Q3. So here Q2 is equal to 2.0193. Q3 is equal to 3.1377. 3.1377. That equal to the final value sigma 2 is equal to 1492 Newton per mm square. 1492 Newton per mm square. Coming to the third one. So here third one, E value is same, 200 into 10 cube. L3 value is different. Here L3 is 200. 1 by 200 into minus 1 into, so third element. So here third element is this one that equal to 3 to 4. The nodes are 3 and 4 that equal to Q3 and Q4. So here Q3 is 3.1377 and Q4 is 4.0688. So here stress 3 is equal to 931. Here stress at third element is 931 Newton per mm square. Coming to the last one, stress at node 4, element 4. So here 200 into 10 cube, 1 by 200 minus 1. So here Q4 and Q5. So what is the Q4 value? So here Q4 is 4.6088. Q4 is 4.6088 and Q5 is 3.5. The stress 4 is equal to minus 569. Stress 4 is equal to minus 569 Newton per mm square. These are the 4 stress values. Some last one, support reactions. support reactions. Last one, support reactions. Last one, support reactions. Last one, support reactions. So here the supports are first one and last one. So here the support reaction formula R equal to KQ minus F. KQ minus F. So here R1 is equal to KQ minus F1. R1 is equal to KQ minus F1. So here 10 power 5 in the global stiffness matrix. So in the global stiffness matrix, so here in the global stiffness matrix, so this is the first KQ. So K into Q, so this is the K value 3.33 minus 3.33 0 0 0, and what is the Q value? So here the Q values are this one, Q1, Q2, Q3, Q4 and Q5. The Q values are Q1, Q2, Q3, Q4 and Q5. And what is the F1 value? So here F1 is 0. So here F1, that is fixed end, is 0 minus F1 is equal to 0. So minus F1 is equal to 0. So here this is the 1, 2, this is the one by 5 matrix, this is the 5 by 1 matrix. So final one, so R1 is equal to, so here Q1 value 0, Q2 value 2.0193, Q3 value 3.1377, Q4 value 4.0688 and Q5 value 3.5. We can substitute this nodal displacement in this Q1, Q2, Q3, Q4 and Q5. So the final value R1 equal to minus 167.33. R1 is equal to minus 672.33 minus 672.33 kilonewtons. 673.33 kilonewtons. And coming to the last one, R5 value. So here R5 value is R5, that equal to KQ minus F. KQ minus F. So here K matrix. So K matrix means 10 power 5 into K value. So here the reactive force at 5, the reactive force at 0, 0, 0, minus 4 and 4. 0, 0, 0, minus 4 and 4. So these displacements are same. So Q1, Q2, Q3, Q4 and Q5. So here the Fi value is also fixed end, that equal to Fi equal to 0 minus 0. So the final value is minus 222.67. R5 is minus 227.67 kilonewtons. This is the stepper bar with a distance of 3.5 mm from the fixed end. from the fixed end. Okay, thank you.